Oftentimes in probability, we're interested in events that have two possible outcomes. So, for example, flipping a coin, you're either going to get a head or a tail. If you're taking a quiz, you're either going to get the answer right or wrong. Let's say it's a multiple choice quiz. You're either going to, if you're interested in quality control, then maybe you have a part that's either defective or not. So there's two possible outcomes. But there are also cases where we're interested only in one possible outcome and then anything that's not that outcome, right? So like in rolling a die, we might be interested in getting a 6. So the outcomes we could be divided into two possible outcomes, either getting a 6 or not getting a 6. So either way, oftentimes we're interested in experiments that have two possible outcomes, and a Bernoulli trial is an experiment with two possible outcomes. So that's what a Bernoulli trial or a binomial trial is. It's just an experiment with two possible outcomes, and it was named after Jacob Bernoulli, who did a lot of work with statistics and with these kinds of problems where there was just two possible outcomes. Okay, now a sequence of Bernoulli trials is called a binomial experiment. So for example, we could have an experiment where we toss a coin 6 times and we're interested in how many times it comes up heads. Each one of those tosses of the coin is a trial, and the whole experiment consists of 6 tosses, and each trial is either going to come up heads or it's going to not come up heads. Okay, so let's define here the properties of a binomial experiment. So the first property is that the number of trials is fixed. All right, so we're going to have, like in our coin tossing experiment, we're going to have 6 trials or some finite number of trials. So we're not just going to keep flipping a coin and flipping a coin and flipping a coin forever. So it's going to be a fixed number of trials. All right, the next property is that there are two outcomes, just like we were saying up above. For a Bernoulli trial, there are 2 possible outcomes. So in a binomial experiment, the outcomes of each trial, there are 2 possible outcomes. And in general, we consider these 2 outcomes as either being success, so success, or failure. Okay. Now, sometimes it's a little misleading. Success or failure has a lot of connotation with it. Success, it's just whatever we're interested in. It's an outcome and its complement. Okay, so the outcome and its complement. So we might define success as finding a defective part, right? We could define that as our success, even though it's kind of a failure. Or we could actually define success of having an engine failure on an airplane. The outcome that we're interested in is actually the failure. So it's a little misleading sometimes, but essentially it's an outcome and its complement. So the opposite of that outcome. All right, so the next property of a binomial experiment is that the probability of success in each trial is the same. So the probability of the second trial doesn't depend on the first, or the third trial depending on the first or the second. All right, they're independent probabilities, which kind of leads us to our next property of a binomial experiment, and that is that the trials are independent of each other. All right, so let's move on to example 1, and we're going to practice identifying binomial experiments given these properties. All right, so we have descriptions of several different experiments here, and let's just try to identify whether they're binomial or not. So the first one is just rolling a fair die 3 times and observing the number of times a 6 comes up. All right, let's go down our list of properties and just check them off and see if they meet that property. So first of all, the number of trials has to be fixed, right? In this case, we're rolling the die 3 times. So yeah, we have 3 trials, right? Fixed number of trials, good. All right, so we're good on that property. The next one, there are 2 outcomes for each trial. All right, well, when we roll a die, we're either going to get a 6 or not. Okay, so essentially, since we're only interested in getting a 6, we can just treat all the other possible outcomes as just not a 6. Okay, so even though there are there's 6 outcomes that could happen, but we're only interested in 6 or not 6. Okay, so we're gonna treat it as if there are 2 possible outcomes. We're gonna define the success as a 6 is thrown, and failure would be not a 6. Okay, so we can make 2 work. Okay, we got that. Number 3, the third property here is the probability of success in each trial is the same. All right, so I roll a die, and there's a 1/6 chance that I roll a 6, right? And when I roll it again, it's still the same. I have the same probability of getting a 6. So that works. All right, so number 3, we can check that off. Number 4, the trials are independent of each other. Well, if I roll the die once, that outcome is not going to affect what happens on the second roll, right? That's what it means to be independent, right? Those trials are not dependent on each other, right? You roll it again, there's still a 1/6 chance of getting a 6. Okay, roll it again, and every time there's going to be a 1/6 chance of getting a 6. So yes, these trials are independent of each other. So because we've been able to check off all those properties, we can say now that yes, this is a Bernoulli experiment or a binomial experiment. All right, so let's take a look at the second one. In this one, we roll a fair die and observe the number of times the die is thrown until a 6 appears. All right, well, let's go down our checklist again. Is there a fixed number of trials? Well, in this case, no, right? I mean, a 6 could appear on the first throw, possibly, or the second, or the third, or the fourth, or it might not appear until the 53rd trial, or the 787th trial. I don't know. We don't have a fixed number of trials. So right away, we know that no, this is not a binomial experiment, and the reason is that the number of trials is not fixed. The number of trials is not fixed. Okay? Let's look at the next one here. Rolling a fair die. Actually, maybe I want to keep as long as I can, I'm going to keep the properties up there. Rolling a fair die 3 times and observing the number that appears uppermost. Okay? So now we're just observing the number. Okay, we aren't really interested in any particular number. So, but that's fine if I look at the first property. The number of trials is fixed because we're rolling it 3 times. So we have a fixed number of trials. But now we don't have 2 outcomes. We don't have anything that's we're not interested in any particular single outcome. We're just observing the number that appears. All right. And it can be 1 or 2 or 3 or 4 or 5 or 6. So this one doesn't meet the second criteria, the second property. So this one is not a binomial experiment because there are more than 2 outcomes. So there are more than 2 possible outcomes. 2 possible outcomes. All right, let's look at the next one. I'm losing my properties, but we know what they are now, right? Good to have these memorized. Our card is selected from a deck of 52 and its color is observed. And then a second card is drawn without replacement and its color is observed. All right, so do we have a fixed number of trials? Well, it appears we're drawing 2 cards. So that's good. Are there 2 outcomes possible for each trial? Well, there's 2 colors, right? It's either going to be black or red. So there seem to be 2 different colors. There's 2 different possible outcomes, either going to be red or black. So that seems to check out. Are the probabilities of success the same in each trial? Well, first of all, we have to define what success is. But we could easily do that. We could call red success and black failure, or vice versa. It doesn't really matter what we call success. But the trouble is that when we draw the first card, there's a 1/2 chance that we're going to get red. Then when we draw the second card, the color that we draw is going to depend on what was drawn in the first. The probability of the color that we draw is going to be dependent on what we drew in the first draw, right? Because if we drew red, there's going to be fewer reds left. And so the probability is going to be less, right? And plus there's only 51 cards left. So here the probability changes with each trial, and it's also dependent on what happened in the trial before. So it really fails both those 3 and 4, which are kind of similar. So I would say no, the trials are not independent. The trials are not independent. Okay. All right. So let's go to the next one. All right. So in this one, we're recording the number of accidents that occur at a given intersection on 4 clear days and 4 cloudy days. So this one right away, I can see that we don't have, the probability of an accident is not necessarily going to be the same on a clear day as a rainy day. So I would say this one fails because the probability of an accident is different for these types of days. All right, and this last experiment, we're recording the number of hits a baseball player makes whose batting average is 0.325 after being up to bat 5 times. All right, so let's go down our list. Is the number of trials fixed? Yes, we have 5 times at bat, so the number of trials is fixed. And the next one is, are there 2 possible outcomes for each trial? Well, every time the batter or this player is at bat, he's either going to get a hit or not. So I would say yes, there are 2 possible outcomes. The next property is that the probability of success in each trial is the same. Now we're given a batting average, and I guess we can assume that batting average is fairly consistent. So I think that we could safely assume that. So yeah, I think that the probability for each trial is the same. And are the trials independent of each other? Well, I think we can assume that. I think we can assume that, his batting average is fairly consistent, and that, maybe he's hit if he didn't get a hit on the last at bat, that maybe that I don't know whether he'd be is that going to make it more or less likely that he would get a hit on another at bat? I don't know. It doesn't seem like it seems like we could safely assume that his batting average is going to be fairly consistent. So I'm going to say that yes, we can consider this a Bernoulli trial. Of course, we have to make some assumptions, but I think those assumptions are fairly safe to make. So we could consider those Bernoulli, this experiment a Bernoulli trial. All right, so I think that's enough for this video, and I will meet you for the next example.